Transformer-less bidirectional grid-connected single power conversion converter. Abstract: a transformer-less bidirectional grid-connected converter is introduced. This bidirectional converter has a bidirectional DC-DC converter and an unfolding bridge, with a single-stage power conversion. Advantages of this converter include single-stage power conversion and usage of low battery voltage. Bidirectional power conversion is done by the bidirectional DC-DC converter due to its adaptive controlling functions. The grid voltage is obtained from the unfolding bridge as it converts the rectified sine wave into the grid voltage. The grid current is controlled with a feed-forward nominal voltage compensator. Therefore, the power conversion efficiency increases. By using this non-isolated topology, the voltage gain in buck and boost mode can be increased. Keywords: energy storage system, S, non-isolated topology, high efficiency. 1. Introduction: bidirectional DC-DC converters are important nowadays due to the increasing need of bidirectional energy transfer. Apart from the traditional applications, the new applications of bidirectional converter include energy storage in interruptible power supplies and renewable energy system. The renewable energy sources like wind, photovoltaic etc. are fluctuating type, hence it cannot be used as a single source of power. Energy storage devices are commonly used to avoid these fluctuations, and it provides a continuous power flow. Batteries are the most economical and commonly used energy storage devices in medium power. For the controlled power flow between batteries and rest of the system, a bidirectional converter is used. In a conventional two-stage bidirectional converter, power is processing in both stages with a high-frequency switching. In a two-stage bidirectional converter, it has a DC-DC converter for the conversion of the battery voltage to DC link voltage and a DC-AC converter for the DC link voltage to grid voltage. Hence, in two-stage converters, two controllers are required for each stage. Thus, the overall efficiency decreases because it is the product of efficiency at each stage. Also, the circuit has high switching and conduction losses, due to gate drive circuits. Thus, conventional two-stage bidirectional converters are not cost-effective, and it has very complex circuit, and thus it is less efficient. 4. In the single-stage bidirectional converter, there is only a single power conversion stage with a single high-frequency switching for the DC-AC power conversion, resulting in higher efficiency, and cost-effective than conventional two-stage converters. Thus, single-stage bidirectional power converters have enhanced system reliability, improved system efficiency, and a less complex circuit than a two-stage bidirectional converter. 1. This paper presents a modified non-isolated single-stage power converter with the same control algorithm. The isolated DC-DC converter is replaced with a non-isolated topology. By avoiding the high-frequency transformer in the DC-DC converter, the high-frequency switching can be avoided, which means the control circuit is less complicated and the overall efficiency and gain of the circuit is improved. The feed-forward control system provides seamless mode transition in charging and discharging modes. Thus, size and weight can be reduced. From the above, it can be inferred that this topology can be developed in a cost-effective manner. 2. Proposed system. The block diagram consists of battery source, non-isolated DC-DC converter, and an inverter. Both are using single power control. The input DC voltage is given to the bidirectional converter by using a battery, where the voltage is stepped up or down to the required voltage level. From the converter circuit, voltage is given to the full bridge inverter. Output AC voltage from the inverter is connected to grid via a filter circuit. A transformer-less bidirectional single-stage DC-AC converter is introduced. The proposed inverter has 7 switches and is capable of working in both buck and boost modes of operation. 3. Operation of the proposed system. Fig. Point 3 below represents the proposed system. Here C3 is the capacitor which links the DC circuit. At the input, voltage is provided by battery which is connected to non-isolated DC-DC converter. Switch S1 to S4 constitutes the unfolding bridge. In the proposed system, a transformer-less topology is used. The coupled inductor is used, which has the primary inductance Lp and secondary inductance Ls is tightly coupled on the same ferrite core, which increases the voltage diversity on both buck and boost modes. D1 corresponds the duty ratio of S11A and DS12, where D3 represents the duty ratio of switch S13. Both D1 and D3 are related to each other by D1 equals 1 D3. The coupled inductor can be assigned as an ideal transformer with the magnetizing inductor Lm and turns ratio N equals N2/N1, where N1 is the primary number of turns and N2 is the secondary number of turns of the coupled inductor. Here input DC voltage is given to the boost circuit where it is stepped up to a required voltage level. From the boost circuit the stepped up DC voltage is given to the full bridge inverter and DC to AC conversion take place. This AC voltage is given to the load via the filter. In boost mode, the non-isolated converter boosts up the low input voltage to high DC link voltage and the switch S2 remains off during this mode. The proposed system has 4 modes of operation. The 4 operating modes are: A mode 1, during MODE1, switch S11 was on, whereas switch S13 was off. Low battery bank voltage is applied to the circuit. Capacitor C2 remains charged before MODE1 and ILM increases linearly. B mode 2, switch S11 turns off in mode 2. The capacitance across switch S11 is charged by primary current ILP, capacitance across switch S13 and is discharged by the secondary current ILS. This mode completes when the voltage across switch S11 is equal to the capacitor voltage Vc1. C mode 3. Since switch S11 is off, due to leakage inductance the primary current ILP start decreasing while the secondary current ILS goes down. Hence, the body diode of switch S13 turns on. Through diode D1 capacitor C1 starts charging because the voltage across capacitor C1 is get lower than the voltage across switch S1. Hence the voltage stress across switch S1 is decreased. D mode 4, during the ZVS switch S13 turns on. For the transfer of energy to the inverter side of the circuit the 2 windings of the coupled inductor and C2 capacitor are all now connected in series. ILS goes up until it reaches ILP, then it follows ILP until the end of mode 4. Thus, the energy stored in both windings are dissipates across the inverter side of the circuit. In this mode D1 and D2 are in off condition. E mode 5, in this mode, switch S13 turns off. The parasitic capacitance of switch S13 is charged by the current ILS. Capacitor C1 starts discharging across capacitor C2, through diode D2. F mode 6, during MODE6, switch S11 is turns on due to the ZVS. Hence S11 is not accepting any current from the clamped circuit, the switching losses becomes decreased due to ZVC, and gets an improved efficiency. The next switching cycle starts when Vc1 equals Vc2, and repeats the cycle. 3 Control section. In this converter the grid current I/O is controlled in the power processing stage. The primary switch duty D can be re-expressed as the sum of 2 duty terms as follows: D equals dP plus .D. dP is the steady-state duty and .D is the control duty. The sign of the reference current Ig determines the direction of the power flow for the selected mode. The control block diagram of the proposed transformerless bidirectional converter is shown in Fig. 4. dP is shared in both charge and discharge modes by using a fed-forward voltage compensator so that an easy control environment is obtained by presetting an operating point. Seamless mode transition can be obtained due to these features. The power flow direction and power value are calculated only by the reference grid current Ig. In a steady-state condition, D is not sufficient to achieve precise tracking because it results in periodic errors. Fig. 4 Control System Block Diagram. So that, a repetitive control duty. DRC should provide better control input responses for the grid current and the zero steady-state error tracking. Therefore the control system is a developed one and is very suitable for reference current tracking and seamless mode transition. 4 Simulation results. The proposed system is simulated in MATLAB/Simulink. The simulation model is shown in Fig. 5.A and 5.B. Figure 5a shows the Simulink model view from battery side and 5.b shows the Simulink model view from grid side. Here 480V DC is provided at the input side. This DC voltage is then given to the boost circuit. From the boost circuit stepped up voltage is given to the full bridge inverter. When simulated output AC voltage from the full bridge inverter is 230 VRMS is obtained. Fig. 8. And Fig. 9 shows the input and output waveform of the proposed system. There is a voltage perturbation is applied on the grid at 1 SEC and the perturbation lasts for 1 second. After 1 S the system regains its original state. Another advantage of proposed system is improved gain. On calculating the gain, the existing system has voltage gain 10 and the proposed system has an improved voltage gain which is equal to 12. 6. Conclusion. A single-stage transformerless DC-AC converter is proposed. It can be used for photovoltaic grid-connected systems and low-input battery voltage applications. In the existing system, transformer used for isolation purpose increases core losses in the system. It also makes the system bulkier and costlier. Increase in core losses reduces efficiency of the system. To overcome this problem, transformer-less topology is adopted. This configuration has higher efficiency. Since transformer is avoided, it reduces the size and weight of the system, making the system efficient and cost-effective. Large voltage diversity is obtained in all modes of operation due to the ZVS operation. This helps the circuit to boost up the low input voltage to high DC link voltage, and vice versa. The control algorithm consists of a feed-forward nominal voltage compensator and a repetitive control scheme. The feed-forward nominal voltage compensator provides an easier current control.